Hello. In this podcast, we're going to meet a statistical technique called maximum likelihood estimation. And this is a very important technique in estimating the parameters of statistical models. And what we're also going to do today is we're going to discuss quite a bit of calculus. So there's going to be calculus in this podcast, and there's also going to be quite a bit of algebraic manipulation. So there's quite a few things that's going to go on. And at the end of the podcast, there's going to be some advanced material. And this advanced material is going to be on the properties of maximum likelihood estimates. And it will link these very briefly to the idea of confidence intervals. So let's move on to another page and talk about what maximum likelihood estimation is, what we're actually trying to do. So let's assume that we have a random sample, and I'm going to denote this random sample as y1 up to yn, and we're going to assume that this random sample comes from a particular statistical model. And our statistical model is going to be based on the normal distribution with location parameter mu, so in fact that's the mean mu, and spread variance sigma squared. So if we look at a picture of the probability density function of a normal distribution, it looks like this. I'm not showing you to draw this very well, but if these are values of y, this is the probability density function, and we write that as f big Y as a subscript y, and the subscript there, the subscript y, is saying that the underlying random variable from which the data y come is called capital Y. So the probability density function of a normal distribution has this bell-shaped curve, and as I said, not very well drawn, but it's centered on mu, and that's often referred to as the location parameter. And its spread is controlled by sigma. So sigma is the spread of this distribution, like I've shown there. And what we have is we collect data according to this distribution, and the data points corresponding to points of high density are the ones that occur most, whereas values in lower density regions, for example the tails, occur less often. So we're going to assume, as I've said, that we've got a random sample from this random variable y, and our task of today is to estimate the location parameter mu. And we're going to do this by using a technique called maximum likelihood estimation. And this is a very important technique that's been used extensively in estimating the parameters of a statistical model. So to use maximum likelihood estimation, we actually need to write down a formula for the model that we're assuming. So we're assuming here that our data come from a normal distribution. So we'll just write that again, because that's a key point. So the data come from a normal mu sigma squared distribution, and we want to estimate mu. And we need to write down, first of all, the probability density function of each data point. So we need to write down a probability density function for that curve. We need the formula for that curve. So we're going to write Fyi of yi. So that's the probability density function for the ith data point yi. And that's the probability density function of a normal distribution with mean, mu, and variance sigma squared. So that takes the following form. So it's 1 over the square root of 1 over 2 pi sigma. Then we have the exp to the minus yi minus the location parameter of interest squared over 2 sigma squared. And yi can take any value between minus infinity and infinity. And our task, as we've already said, is to estimate mu. So what we have now to do is to write down the probability density function of the full data set. So I'm going to do that on the next page. So now we're going to write down the probability density function of the full data set, which is y1 up to yn. So that is the probability density function y1, yn at the observed values y1, yn. And then we can actually work out what that is. We're going to use the fact that each of the data values is observed independently, and that's because we're assuming a random sample. So we're going to use independence due to random sample, and that means we can multiply the individual probability density functions in the way I'm writing here. So we've got each individual probability density function for each individual data point can be multiplied together in the way illustrated. So that means that on the left-hand side, I've got the probability density function for all the data that we observe, and our assumption of independence has allowed us to write that in a very simple way, or in a much more simple way, on the right-hand side. And we can use the product notation to simplify what we've written. So that's the product from I equals 1 to n of Fyi evaluated at the data point yi. So we're multiplying together the n individual probability density functions. Now, on the previous page, we had a formula for each of those probability density functions. So I'm going to now substitute that in. So we had the 1 over root 2 pi sigma. Then we have the exp of minus yi minus the parameter of interest mu squared over 2 sigma squared. And then we can use the rules of multiplication to write this in a simpler way. In the first term here, this one here that I'm now circling, that's a constant as far as I is concerned. Doesn't depend on I. So if we multiply a constant by itself n times, we just get the constant raised to the power n. So that's 1 over root 2 pi sigma raised to the power n. And then we have an exponent here. We have an exp. And it's a fact that if we look at the exp of A times the exp of B, then that is equal to the exp of A plus B. So we can add the exponents. So that means we end up here with exp of adding up the exponents. We just need to bring in there a sigma term to add up all those terms there. So that's a simplified version of this joint probability density function of all the data. And I'm going to write that in a slightly more simple way by working a little bit with this initial constant out the front here. And what I'm going to do is I'm going to bring the sigma squared in this, sorry, I'm going to bring the sigma in the square root, and it will become a sigma squared. And then I'm going to write everything as, instead of to the power n, to the power with a negative sign to get rid of this 1 over. So in fact, that first term I'm going to write as 2 pi sigma squared. So I've brought inside the sigma squared. But now I've got the square root, so that's going to be a half. So I'm going to get minus, because it's 1 over n over 2. And then I've got exp of this sum of the yi minus mu squared over 2 sigma squared. Now, we're interested in finding mu. We're interested in estimating the location parameter of this normal distribution from the data. So our interest is mu, and therefore we think of this here as a function of mu. So this is thought of as, or written as L mu, and L means likelihood. So L mu is referred to as the likelihood of mu. So what does this mean? Well, let's move on to another slide and draw what the likelihood could possibly look like. So the likelihood could look something like this, or does look like something like this. So here you have mu, here you have L of mu, and that function as a function of mu looks a bit like this. So what is this function of mu, this likelihood function of mu, measuring? So its value at any particular value of mu, so that of course is L mu, at that particular value of mu, that's a measure of how likely the data are when the parameter of interest is mu. So it's a measure of how likely the data are when the parameter of interest is mu. And that motivates our estimate of mu as the value that maximizes this likelihood. So on this picture, the value that maximizes this likelihood is indicated there, and that value, of course, because it corresponds to a maximum, corresponds to a point on the function of 0 slope, and this is a sensible value to choose because under this value the observed data are most likely. Okay, so, and why does that make it sensible? Well, the only thing that you actually have is the observed data. That's what you've got, that's what you've observed. So it makes sense to have a model that says the observed data are most likely. So our task now is to find mu hat. So what we want to do is we want to find the value of mu, the value of this parameter mu, such that that value maximizes the likelihood function. Now, because the likelihood function has the exp in it, the exponential function, it's quite a hard thing to maximize. We're going to maximize it by calculus, but first of all, we're going to use a technique which is often used when maximizing likelihood and other functions, and that technique is we're going to take the log. Now, it actually turns out that the value that maximizes the likelihood big L of mu is the same value that maximizes the log of big L of mu. So let's say that the mu hat that maximizes L of mu is the same value that maximizes log L of mu. And if we think about the big L of mu, we'll work with this very soon, but there was the exp. Taking logs gets rid of the exp and makes our life simpler. So that's the motivation for working with log of a big L mu. And log of big L of mu is written little l of mu. And that's referred to as the log likelihood. So when we're wanting to maximize this likelihood function, it's mathematically easier to maximize the log likelihood function. And you might like to think about why what I've just said is correct, why we can work with the log and not the original function. And the basis of the reason is that if we have a number a that's less than b, then the log function preserves that relationship. So log a is less than log b. So now we're going to get to work and we're going to use some algebraic manipulation and calculus to actually find an expression for this mu hat. That's the value at which the likelihood function L and the log likelihood function little l are both maximized. So we've established before that little l is the log of the likelihood function, and we're now going to actually work out what that is. So that's the log, and let's write down the expression for the likelihood function that we found before. So that's 2 pi sigma squared to the minus n over 2. The exponential of minus the sum I equals 1 to n yi minus mu squared over 2 sigma squared. Now, it's a fact of logs that if you have the log of the product, the log of AB, that's the sum of the logs, log of A plus the log of B. So what we can do now is we can split this log here up because we've got the product of two terms. There's one term there, and this exp term is the other term there. So now we can split this log into the log of 2 pi sigma squared to the minus n over 2 plus the log of the exp term. So it's exp minus and this quadratic term here. Okay, and it's also a fact that a log is the inverse function of exp. So when we apply log to the exp, they effectively cancel each other out. And that gives us that the log of the likelihood is just the log of the first term and then we just have minus coming from the exp term of the sum of yi minus mu squared over 2 sigma squared. So what we have is that the log and the exp have cancelled each other out, and we're actually left here with a quadratic function of mu. So there's mu, there's the square, so we have a quadratic function of mu. Okay, so let's move on to another page and let's actually draw that quadratic function of mu. So here we have again the axis, here we have the little l, the log likelihood of mu, and we've seen that that's a quadratic function of mu. We haven't actually seen whether it looks like that or like that, and I'll come on to that later, but let's just assume it looks like that for the moment. And our task is to find the maximum that corresponds to the point of zero gradient, and that value at the maximum is called mu hat. So we're seeking the value of mu hat such that at that value the gradient is 0. So let's do some calculus. So here we have again the expression for L of mu. So what I'm doing is I'm using the formula that we had before, but I'm going to take the power down from the log, but that's not important. So it's minus 1 over 2 log 2 pi sigma squared. But what is important is this term here, sigma I equals 1 to n yi minus mu squared over 2 sigma squared, because that is the only term there that depends on mu. Now, I'm going to differentiate this with respect to mu. So I'm going to work out d by d mu of this log likelihood term. Now, the first term is constant with respect to mu. So when I differentiate a constant, I get 0. Therefore, the whole likelihood is just minus d by d mu of the second term. And you'll see there that I've actually pulled the d by d mu in front of the minus sign, and that's perfectly legitimate step. You can bring the derivative in front of a sign. And we can also now do a bit more. We can do 2 further stages. We can bring the constant outside the derivative, and the derivative can also pass in through a summation sign. So we actually end up with minus 1 over 2 sigma squared, so that's bringing the constant outside, and now I'm bringing the derivative inside, so that's sigma I equals 1 to n d by d mu of yi minus mu squared. So my next task is to actually perform that differentiation. So I'm now going to work out d by d mu of yi minus mu squared, and that's quite a standard thing to differentiate. We differentiate that using the chain rule, but I'm actually going to do that without writing out the details of the chain rule. What we end up doing is we just differentiate that in a sort of normal way, so we get 2 yi minus mu, and the 2 gets reduced to the power 1. But then we've also got to multiply that by the derivative of the inner term, and that could be minus 1. So that minus 1 is the derivative with respect to mu of yi minus mu. So when we bundle all this together, we end up with minus 2 yi minus mu. So the derivative of the term inside the sum is minus 2 yi minus mu, and therefore the whole thing ends up equaling minus 1 over 2 sigma squared, sigma I equals 1 to n of minus 2 yi minus mu, and then we can do some cancellation. The minus signs cancel, and the 2 on the top and the bottom cancel. So we actually end up with 1 over sigma squared, sigma I equals 1 to n of yi minus mu. So that's an expression for the first derivative, the slope of the log likelihood function at any value mu. Now, we seek the value mu hat such that at mu hat the slope is 0. So we're seeking this value mu hat such that the first derivative is 0. And that means, using the expression on the previous page, that we're seeking the value 1 over sigma squared, sigma I equals 1 to n yi minus mu hat equals 0. So we're just taking the expression that we formed on the previous page for the derivative of the log likelihood function and evaluating it at mu hat, and that's the value such that the derivative is equal to 0. Now, we can get on and solve this for mu hat, because the constant there can be multiplied through and therefore disappears. So that's the same as sigma I equals 1 to n yi minus mu hat equals 0. And then we can expand this sigma, so we end up with sigma of the first term minus n mu hat, because we're summing together n lots of mu hat, and that equals 0. So let me just explain that in a little more detail. If we say sum I equals 1 to n mu hat, then what that really means, that's mu hat plus mu hat plus mu hat, and there are n lots of those, and that is equal to n mu hat. So therefore, we end up with the sum I equals 1 to n yi is equal to n mu hat, bringing the n mu hat to the other side, effectively adding n mu hat to both sides, and then finally we can divide both sides by n to get that the sum I equals 1 to n yi when divided by n is equal to mu hat. So our maximum likelihood estimate is mu hat equals the sum of the data points that we've observed divided by n, and that's written sometimes as y bar, and is said to be the sample mean. Okay, so at this point, although I've called it the maximum likelihood estimate, we don't actually know that it corresponds to a maximum of the likelihood. It could be that it corresponds to a minimum of the likelihood. So what we have to do is we have to do a further check to see whether this point actually corresponds to a maximum. So think about how we can do that. And this again illustrates a standard piece of calculus. Here we have again the log likelihood function. Now, we've found a point at which the gradient is 0. So we found this point here, mu hat, at which the gradient is 0. We don't at this point know whether that corresponds to a maximum or a minimum. When we have a maximum, we have a positive gradient followed by a negative gradient. So this means that there's a decrease in the gradient itself. So what we need to do is to check whether we have a maximum. We look at the change in the gradient. So the change in the gradient. And we hope that that change in the gradient is negative. So a negative change in the gradient, that means we have a maximum. So this is the gradient, and this is the change in the gradient. And if the change in the gradient at the point of interest, mu hat, is negative, then mu hat corresponds to a maximum point. So our task, therefore, has to be to work with the change in the gradient. Now, change in the gradient sometimes is written as d2 by d mu squared. So what we have there is d2 by d mu squared, L of mu evaluated at mu hat. So therefore, our next task is going to be to work out d2 by d mu of L mu hat. So we do that on the next page. So we've already seen that the gradient d by d mu of L of mu is equal to 1 over sigma squared, sigma I equals 1 to n yi minus mu. And we set that equal to 0 and found a mu hat. But now we're going to work out d2 by d mu squared of L mu. And that's just found by differentiating with respect to mu the right-hand side. And the same rules apply as before. The constant can be moved out, and the differential operator can be moved through the sum to go there. So we actually have 1 over sigma squared of the sum I equals 1 to n of d by d mu yi minus mu. And then when we differentiate yi minus mu, well, when we differentiate yi, we get 0, because it's a constant with respect to mu. And when we differentiate minus mu with respect to mu, we just get minus 1. So what this term here, the differential part, is equal to minus 1. And we have something like we saw before. So we have 1 over sigma squared, the sum I equals 1 to n of minus 1. And if we add up minus 1 n times, we end up with minus n. So the second derivative at any point mu is minus n over sigma squared. Now, n is the sample size, so it's a positive integer. Sigma squared is squared, so that itself must be positive. And so we end up with the negative of something positive, so we end up with something that's negative. So the second derivative of the log likelihood function is negative, and that's exactly what we wanted, because we now know that the second derivative of the log likelihood function evaluated at the point mu hat, sample mean, is negative, and that means that mu hat in fact does correspond to a maximum. And therefore we have found and demonstrated the maximum likelihood estimator of the location parameter mu of the normal distribution. So I'm just going to conclude there this first part, that the value mu hat, which is the sample mean of the observed data, which sometimes is written as y bar, that is the maximum likelihood estimate of the location parameter mu of a normal mu sigma squared distribution. And in theory, this idea of maximizing the likelihood, that is finding the parameter value that makes the data most likely, can be used to estimate the parameter or parameters of any statistical model. In practice, very often numerical techniques have to be used because it's too difficult to do calculus to find the maximizing value. But the principle is the same. To estimate the parameters of a statistical model, you write down the likelihood, you take the log of the likelihood to make your life easier, and then you use either an algebraic technique or a numerical technique to work out the value of the parameter or parameters that maximizes that log likelihood. So that's a very powerful idea in statistical modelling, and today we've met one example of it. So that ends the first part of this discussion of maximum likelihood estimation. The next part is more advanced material, and it's going to be about the sampling distribution of the maximum likelihood estimate. So I'm going to use a new page for this, and this is, as I said, advanced material. In the sense that it's a step on from actually working out the value of the maximum likelihood estimate, we're now going to look at some of its properties. So what we had is a statistical model that said yi is normally distributed with mean mu and variance sigma squared, and this distribution was independent across all i's. So all our data points are assumed to be independent. And then we had an estimate of mu, which takes the form given here, the sample mean. So that's y. Okay, now we can ask ourselves, what do we expect the value mu to be? So that should have been, what do we expect the value of mu hat to be? So we can actually work that out. That's the expected value of sigma I equals 1 to n yi over n. And expectation is very similar to differentiation. A constant can be pulled out, and the operator itself can be pulled in. So we end up here, I'll do it in two steps, as 1 over n, the expected value of sigma I equals 1 to n yi, which is equal to 1 over n sum I equals 1 to n expected value of yi. Now, we know what the expected value of yi is because under the model up here, it's mu. Mu is the expected value of yi. So we can just substitute here mu, so we get 1 over n sum I equals 1 to n of mu, giving us 1 over n. Now when we sum up a constant n times, we've seen twice already, that's just n times the constant. So we end up with just mu, because the n's there cancel. So what we have is that the expected value of mu hat is equal to mu. And this means that on average, the maximum likelihood estimate mu hat is the value mu that it's trying to estimate. So we say that mu hat is an unbiased estimator of mu. Now, what does that mean? Mu hat is an unbiased estimator of mu. Well, it means if we do the following procedure. If we take a sample of data, and if we then use that sample of data to work out the estimate mu hat, and then if we repeat that procedure an infinite number of times, then we end up with an infinite number of different estimates mu hat. So each of these mu hats comes from a different data set and therefore will be different. So we end up with an infinite number of possible estimates mu hat from an infinite number of data sets, and the average of these values will be mu. So that's the average of those values mu leads us to say that mu hat is an unbiased estimate of mu. And another way to think of that is perhaps to think of it as in a sporting context. Sometimes the referee favours one team, sometimes the referee favours another team, but on average he doesn't favour either of the team. So sometimes the mu hat estimate will be too low, so it may be less than mu. Sometimes the mu hat estimate will be more than mu. But on average, it is mu. And this property of having an unbiased estimate is one that sometimes we look for as a good thing when we're talking about the properties of an estimate. Okay, so the question that we can ask ourselves is how spread out are those mu values? So we can ask ourselves, what is the variance of our estimate mu hat? And this also illustrates properties of the variance. So that's the variance of 1 over n sigma I equals 1 to n yi, because mu hat is the sample mean. And then a property of the variance says we can take out a constant, but we have to square it. That's because variance is basically a measure of a squared quantity, the squared deviance from the mean. So it's defined in terms of a square, and then when we take out the constant, we have to take notice of the fact that the square is in the variance definition, and so we have to square it. So this variance here is 1 over n squared, the variance of sigma I equals 1 to n yi. And because the yi's are independent, we can pass the variance through the sum. We couldn't do that if the yi's were not independent. So independence is absolutely necessary to allow us to take the variance through the sum. So this is 1 over n squared, the sum I equals 1 to n, variance of yi. And we've seen above that our model assumes that yi follows a normal distribution with mean or location parameter mu and variance sigma squared. So we can now replace this variance yi with sigma squared. And so we end up with the variance of mu hat is 1 over n squared, the sum I equals 1 to n sigma squared, and the sum I equals 1 to n sigma squared is n sigma squared for exactly the reasons we've seen before. So we end up with 1 over n squared times n sigma squared, and the n on the top cancels out with one of those n's on the bottom, giving us sigma squared over n. So the variance of mu hat is sigma squared over n, and that's a very important result for us. And what's really important about it is the fact we have this over n on the bottom. And that says that as the sample size increases, so as you take more data, there will be less variability in your estimate. So you're better off taking more data. So what we see is that the variance of mu hat, the spread of mu hat, the the lack of reliability in mu hat decreases as n increases. Now, if we take the square root of the variance, we get the standard deviation. So the standard deviation of mu hat is just the square root of sigma squared over n, which is sigma over root n. And that's a quantity that comes up a lot when we look at confidence intervals. But the standard deviation of mu hat is sometimes referred to as the standard error. Okay, so those are the properties of the estimate mu hat. We've worked out the expected value, and we've seen that the expected value is mu, so that mu hat is an unbiased estimator of mu. And we've also worked out the variance or spread of all the possible mu hats, and we've seen that decreases as sample size increases. And that's a good thing, because it means we get more reliable as we collect more data. We can link these ideas a little bit to the ideas of confidence intervals. Let's, to do this, begin by just reminding ourselves that the variance of mu hat is sigma squared over n. We found that on the previous page. And also we found some time ago that the second derivative of the log likelihood evaluated at mu hat is equal to minus n over sigma squared. So you can see straight away that there's a relationship between those two quantities. The same essential quantities are appearing in both parts of this. And what we can deduce from that is that in this particular case, it doesn't hold for all models, but it does hold in this case, the variance of the maximum likelihood estimate is equal to 1 over the absolute value of the second derivative evaluated at that maximum likelihood estimate. So the absolute value gets rid of the minus sign, and the 1 over turns the n over sigma squared into sigma squared over n. So that's a fact that applies in this case that has implications in the theory of maximum likelihood estimation. And now we can think about the relationship with confidence intervals. So what I'm going to do is I'm going to draw two pictures, picture 1 and picture 2. And both these pictures are going to be of log likelihood functions. So here we have the axes being set up, and we're going to look at two cases. So in the first case, so these are going to have the same maximum. In the first case, we're going to have a very wide quadratic function, so something like that. Whereas in the second case, we're going to have a much narrower quadratic function for the log likelihood. So maybe something like that. And both these are going to have the same maximum at mu hat. So we know at mu hat the gradient is 0. So again, the same thing applies here. And in practice, picture 1 is the sort of picture you get when you have a small sample size. And picture 2 is the sort of picture you get when you have a large sample size. Okay, now let's think about the value of d2 by d mu, the second derivative at the log likelihood of the log likelihood at the maximum likelihood estimate. So in this case here, we know it's going to be negative. And it's negative because we're changing from a positive gradient to a negative gradient. But here the change is quite slow because we're going up slowly and then down slowly. So what we're going to find is that the second derivative is going to be small and negative. Now, in this second case, we're going from positive to negative gradient, but we go up quickly and we come down quickly. So in this second case, the second derivative evaluated at the maximum likelihood estimate is going to be large and negative. And if we now drop down a line the same height above the maximum, so we're going to drop down a line the same height above the maximum, and we're going to look at the interval that that line cuts off. So there's the interval. Then that interval there is an interval of possible mu values of high likelihood. And again here we have an interval of possible mu values of high likelihood. Now it turns out, and we aren't going to go into the details of this today, that that interval is called a confidence interval. And what we find is, in this case here, the confidence interval is wide. So here we have a wide confidence interval. And again, that's because there's a slow change in the log likelihood function. Here we have a narrow confidence interval. And again, that's because there's a quick change in the log likelihood function. Now let's try and link this with the idea of variance that we saw before. Now when we've got d2 by d mu of L mu hat, the second derivative, is small and negative. Well, when we take the absolute value of that, the negative goes away. And when we take 1 over small, so when we have 1 over small, that's big. So this means that the variance of mu hat is going to be big. And that makes good sense, because we've seen that the associated confidence interval is wide. So a big variance means unreliable, which means the confidence interval is going to be wide. And the opposite applies when you have the second derivative being large. Then what you have is the negative is removed by the absolute value, so you end up with 1 over large, and 1 over large is small. So in this case, the variance, how much it's spread out of the maximum likelihood estimate, is small. So the maximum likelihood estimate is essentially reliable, and that's linked very nicely to the idea of having a narrow confidence interval. So this extra material here was to try and link in some intuitive way these ideas of maximum likelihood estimation and variance and the log likelihood function with the idea of confidence intervals. So just to summarize what we've done in this podcast, we've derived in detail the maximum likelihood estimate of the location parameter mu of the normal distribution. And that's led us to look at a general technique for estimating parameters of a statistical model. And then, as additional advanced material, we've actually derived some properties of the maximum likelihood estimate, and we've linked the second derivative of the log likelihood function to the variance of the maximum likelihood estimate, and to the idea of confidence intervals of various widths. Thank you very much.